Hello, today I'll be presenting my HDR imaging and tone mapping implementation for AI621 Assignment 3. I'll show you how I created the high dynamic range images from both RAW and JPEG exposure stacks and evaluate their quality and quantitatively. Then I also implemented 3 tone mapping algorithms to compress the dynamic range for display. Let's start with the HDR image creation. So for RAW files, I used the DC RAW, dcraw with the -4 flag for linear 16-bit output and -Q3 for AHD demosaicing and the -W for white balance. And you can see this in the convert raw to TIFF DC raw script, which batch processes all 16 exposures, giving us a true linear sensor data for 4016 by 6016 resolution. Now for JPEG images, I implemented the Devivetch malloc algorithm in this script, as you can see on the right-hand side, and the recover response curve function, as you can see here, starting at line 88. It builds a sparse linear system with 456 unknowns and 256 values for GZ mapping, pixel values to log radians, plus 200 log radiances for at sampled pixels. I sampled 200 random pixels across 16 exposures, giving about 2,400 data equations, and I add 254 smoothness equations penalizing the Laplacian, and one constraint fixing g of 128, which is equal to 0. And this is done so by solving with SciPy's least square, which gives us smooth monotonic response curves with residuals around 33 to 35 per channel. So if you look at figure 1 here on the left-hand side, we can see that the recovered curves of RGB channels are smooth and monotonic as expected. And the right-hand panel shows expression of exponent g representing the inverse response function. So using these curves, I linearized JPEGs with L linear of exponent of g of L, which is in the linearized image script, as you can see here. And for the weighting functions, this is implemented in uh, the weighting functions.py script, as you can see here. And I implemented 3 schemes, uniform, tent, and Gaussian. And if you look at figure 2 here, which is the weight functions plotted, the tent function peaks at 0.5 intensity, and the Gaussian provides like a smoother fall off, and both downweight dark and bright pixels where noise and saturation are very problematic, and I use tent for response recovery and tested both the HDR merging. Now, if you look at the HDR merge script on the right hand side in the code base here, I implemented 2 merge methods. So linear merging, it does weighted averaging in both the radiance domain and which is physically accurate. And then the HDR log, which averages logged in the log domain, and then exponentiates, which is very perceptually motivated, as we discussed in class. And the key detail is that the weights are computed from the original LDR pixel values and not the linearized ones. So for raw, like unsigned int 16, I normalized by 655335. For JPEG of unsigned int, I go by 255, and this is so that it ensures the weights reflect actual exposure quality. So with 2 sources times 2 methods and 2 weighted functions, I generate 8 images using the create HDR image script here. And if you look at figure 3 on the left hand side of the report, here's a tone map preview of all the 8 generated images. And you notice that the raw based images in row 1 and 2 show significantly better quality than the details and the JPEG ones in row 3 and 4. And the left column uses tent weighting and the right one uses Gaussian. And so given this, how do we evaluate this, right? So to quantitatively evaluate linearity, I use the color checkers 6 neutral gradient patches and evaluate HDR, as you can see here. And if you look at figure 3, which is like the main HDR comparison, the tone map preview of all 8, sorry, Sorry, these patches double in reflectance, so log luminance should form a straight line and in the perfect like linear HDR image. So in this figure, which we plot the main evaluation, the upper curves are the raw based and lowers are the JPEG based. And the raw images show like near perfect straight lines, like almost R squared, which is greater than 0.992, at best, which is the HDR raw linear tint.hdr. Uh, achieves about 0.9929 and the MSC of 0.0033. And so these images also have exceptional dynamic range, which is over like 17, above 17 magnitude, orders of magnitude. Now, if we look at the results, the quantitative results, all four um, raw based, uh, you can see that the raw variations excel and JPEG based images show slightly lower linearity. So R squared from 0.18 to 0.85, and this is mainly due to the lossy compression and gamma encoding. And the best JPEG uses log merging with Gaussian weighting of R squared, which is about 0.8475. And this clearly validates using raw sensor data for HDR image quality. So I'll use the HDR raw linear tint. Uh, this one, sorry, the HDR raw linear tint highlighted here for all tone mapping experiments. So now for the tone map, uh, Reinhard script, I implemented the Reinhard's photographic tone mapping. So the algorithm computes log average luminance as well as scene adaptation point scales by the parameter K specifically. And then we compress the highlights with the burn parameter B. So if you look at the Reinhard photographic, the luminance method here, the top row shows the key parameter variation, so K at 0.09, which definitely gives up slightly darker images, as you can see, and K being 0.36 yields a much brighter image. In the bottom row, it shows the burn parameter effects on the high compression, so K at 0.18 to 0.95. So 0.18 to B of 0.95, which gives the best balance of the scene. Um, I implemented two methods, so per channel RGB and luminance only. Uh, the luminance only approach converts RGB to XYZ and tone maps only to Y while preserving the chromaticity, and then we convert it back. So notice how the right image has slightly better color fidelity, so no color shifts in the neutral areas, and that plague like the per channel method on the left. All in all, the random method is very fast, so it's almost near instantaneous, but also as a global operator, it can't really preserve the local contrast, as well as edge preserved methods. Now, in the tone map bilateral script, as you can see here, I implemented the Durand and Dorsey's, like the edge preserving approach used in the base detail decomposition. So if you look at the bilateral tone map base detail, right, yeah, in the script, if you look at the bilateral base tone map detail in the main method, the function separates the log image into the base large scale and detailed fine scale layers using the OpenCV's bilateral filter, and then we compress the base layer, and then we combine it. So I think a clear representation is in figure 8 here. So here the scale parameters S controls the compression. So S is 2 preserves the more dynamic range but darker shadows. When S is 4, when S is 4, it's much flatter. When S is 3, it's some of like the sweet spot, as you can see. In figure 10, it's sort of like a method comparison between Reinhard, which is bilateral filtering. So compared to Reinhard, bilateral filtering excels at local contrast preservation. And notice how the bilateral results on the right, both like bright, like outdoor area, like the outdoors area here, and the dark regions are somewhat visible. Uh, but sharp edges, like the book, uh, like remain. Sorry, the sharp regions like the book remain like crisp. right? So this is some of like a edgeware filtering uh, uh, that smooths large-scale variations while preserving the details, as you can see. Now, for the bonus implementation, I implemented the Fatal et al. Gradient domain compression. This can be found in the TOMAP gradient domain script right here. The key insight is that large gradients cause dynamic problems, so while small gradients like fine detail should be preserved. And the pipeline extracts luminance in the first step, and we compute the gradients with forward differences, attenuate large gradients using phi. And then we reconstruct the image by solving the Poisson equation. So if you look at figure 11, which displays the alpha variations, alpha really it controls aggressively how we uh, compress the large gradients. So when alpha is like 0.1, it's like aggressively flat compared to like 0.3 being slightly more conservative. So 0.2 is, I think, is like the sweet spot. And in my opinion, the challenging part was like solving the Poisson like iteratively. And so in the solve Poisson iterative like function here, reconstructing from like the modified gradients, it requires solving the Poisson equation for 24 million pixels. And so I built the sparse Laplacian using the SciPy sparse um, sorry, SciPy sparse diax with a 5-point stencil, and then solve the conjugate gradients about 500 iterations. Yeah, and if we look at figure 12, which shows all the different tone mapping methods, Reinhardt on the left is fast, but global. Bilateral in the center has a good local contrast, but takes about 1 to 2 minutes. And gradient domain on the right achieves the best quality, as you can see, like with the darker regions, but no visible halos, but it's quite slow. So the fine textures stay sharp, but only the gradient magnitudes and their locations. Yeah. So to summarize, I implemented the complete HDR pipeline with the raw and JPEG linearization through HDR merging, and we evaluated it, achieving about R squared of 0.99 with about 17 orders of magnitude of dynamic range, and then implemented the 3 tone mapping methods, the Reinhardt for speed, bilateral for local contrast, and gradient domain for highest quality with no artifacts. So please feel free to run the code base, and yeah, thank you for listening.